Question number 3, we have ethane reacting with chlorine to form chloroethane. This is very clearly a free radical substitution reaction because you are dealing with an alkane chemistry. So alkane contains only carbon-carbon and also carbon-hydrogen bond. These are strong bonds. They are considered non-polar, so you're not going to be attacked by a nucleophile. Neither do you have double bond that can attack electrophiles. So the only thing you can go through is substitution, and you're going to substitute out with free radical. That's why it's called free radical substitution mechanism, as you have learned this as your AS case study mechanism. Of course, as with any of the A-level chemistry mechanism, feel free to browse through my topical playlist on the A-level concept videos. Under organic chemistry, there are all the 5 mechanisms, each of which I outlined in a separate tutorial video with example of my choice. And of course, you need to practice drawing it out for yourself with an example of your choice as well. Now use bond energies in order to calculate the enthalpy change for this reaction. You will do well to notice that all of these are in the gaseous state. That means we can use bond energy. We know that our bond energy in the use of calculation for enthalpy change is going to be the bond energy broken. So there's the reactant side. And I need to have minus the sum of the bond energy formed on the product side. So I break this thing and I form this thing. Now you could also be thinking about this in a simpler sense, because I do not really want to break everything, because I can, but then it will be a waste of time. If I purposely draw this as a display formula, then you can see, hopefully, that we are not actually breaking everything, because we can do much better than that. We can see that, let's say this blue color one, I am breaking that and I'm breaking that. I break that and I break that. Why? Because now the CH becomes CCl. So technically speaking, I am forming the CCl and then I'm forming the HCl. So I just need to break one of the CH, one of the ClCl, one of the CCl, and one of the HCl. These two are being formed, these two are being broken. So going straight to my data booklet, so find the bond energy. In the new syllabus, in the new specification for your exams, you will have the data inside the question paper itself. So, it wouldn't make too much of a difference. You still have a data to do your calculations where the question is needed. So find the CH first. That is given as 410. So 1 times 410 plus breaking the 1 times ClCl. That thing is 242. And then use bracket very wisely, close them up, and then minus the sum of the bond energy formed. You're forming one of that CCl. The CCl is 340, so 1 times 340. And then you have one of the HCl. So the HCl bond energy is 431. So I'm going to sum up this side. So 410 plus 242, that is 652. And then minus the other side, 340 plus 431, that is 771. So press that to your calculator. Do not forget the enthalpy change has a sign, has a value, and has a unit. The problem with the sign is when it is positive, your calculator will not show you, so you need to keep your eyes out for enthalpy change, having sign, value, and also unit. So this is minus 119 kilojoule per mole. Now for that 3 marks, some students will have been taught that you need to break everything, including all the CC single bond and the CH one. And here you're forming the CC single bond and 5 of this CH again. So you just be wasting time in these sort of questions. Free radical substitution, where you just substitute one thing here. You don't really need to break everything. There are cases where you do need to break everything that you see, such as combustion. So combustion of alkane, for instance, you get carbon dioxide. That means you must have break every single thing in here. Those are one of the few cases where you do really need to break everything. Okay? Now state the conditions for this reaction to occur. As I mentioned, it was a free radical substitution reaction. So you need your ultraviolet light. So ultraviolet, abbreviated as UV light. And what else? State the conditions needed. That's all really. Okay, so the UV light is essential for this reaction. What we have is this chloroethane, 2 carbon hydrogen alkane, chloroethane, being formed from ethane molecule. And we're going to use a series of equations. This is a 5-mark mechanism. Now you're gonna have an indication of how butane can be produced as a minor byproduct. This will be in your termination steps. So my first step is what I would call initiation. Initiation is basically the homolytic fission. So this is the homolytic because it's the equal breaking of the covalent bonds such that you get Cl like that, half-headed arrow. They call it a fish hook arrow, half-headed because one electron goes here, one electron goes there, and you get Cl dot. This is called a chlorine free radicals. So homolytic fission, equal breaking of these covalent bond such that the bonding electrons are shared equally or are split equally. Homolytic fission of the Cl2 to give or to form chlorine radical. So this is called radicals, free radical, species with an unpaired electron like that. The next step would be your beginning of propagation. You must show at least 2 propagation steps. So let me start with CH3, then I add it with Cl dot. That is going to give me CH3, CH2 dot on the carbon. And now the Cl dot will have formed the HCl by taking away one of the hydrogen. But then I have not shown the formation of chloroethane from my propagation. So I need to show the formation of my desired product in my propagation step. Having done that, I also generate another chlorine radical, and this chlorine radical can attack more of the original ethane, and it's like a cyclic loop kind of thing. That is why it's called a chain reaction, because it just keep on reacting without much control, to be honest. Now, in terms of the last step, it's called termination. Termination is basically radicals recombine. So you will see that in the propagation step, you will have a one radical on the left. So no radical plus radical, giving you radical and no radical. You have one radical on the left and you have one radical on the right. That is the signature of propagation, radical forming radical. Termination is the opposite of initiation. While initiation requires UV light, that means you have high activation energy. Termination is one step with lowest activation energy because the radicals recombined to give molecule. So molecule is not species with unpaired electron, they are just molecule because the radicals recombine. So example, you want butane to be produced as a minor product. So I will get CH3, CH2 dot. So usually I will show the formation of this in the termination step. However, they want the formation of butane as a minor byproduct. So I just have another of this radical and radical. They can combine to give you CH3, CH2, CH2, CH3. This is the butane minor byproduct because your intention really is to show the termination step forming the desired halogenoalkane. Let me see if I can move this up here. So there's your propagation step, and I'll have one more line which I can write my termination there, and they will look a bit neater, I hope. I think. Where does that come from? There's give. Nope, that doesn't look so well. Just give me a minute. All right, okay, that looks better. Of course, I can write another termination step. So the CH3, CH2, usually I will use it to form the desired product as well. So you can see that there is a similarity between this termination step to form this product versus this propagation step to form this product, in the sense that we get the product formation, but in 2 different steps. Here is radicals and radicals recombined. I don't get any radical on the right side, but here I get radical on the left, I get radical on the right side as well. In this next question, we have chloroethane. This is one question where I'm going to draw some skeletal formula. CH3, CH2Cl, C2H5Cl, and then I get this ethane. This is ethane molecule. I have chloroethane on the far left. Now what do I have here? So what am I going to do? Chloroethane can be converted via an intermediate compound. So I guess I could convert it via this. And then I could reduce that. So I could eliminate that. So if I go from here to here, this will be elimination. elimination of your HCl by using NaOH in ethanol. And then from this alkene, I can then go back to the alkane. This is addition of hydrogen, or what I should normally call it would be reduction, where you reduce, where this above the carbon, gain hydrogen. Catalytic hydrogenation is the name of the reaction, but the type of reaction is undoubtedly called reduction there. Any other way you can do this? There could be another way. There will be Cl, and then you could get OH, and then you could get like that. No, but that is not the alkane, that is the alkene, because here I have done substitution. This is hydrolysis or substitution, and this one is done in NaOH aqueous, so that means it's not in ethanol, and then you have to reflux that, and then you minus H2O, that is your elimination of H2O, and they'll give you back your alkenes, and then only then you can get the alkane by doing H2 and nickel catalyst. There will be your reduction step there, so there will be a reduction, but you can see that that is more than one step. There's 1, 2 and 3 step. Here is just 1 and 2 step, and this is as stated in the question, so I can't really do it via this thing first. I just have to eliminate the HCl, and then I do a catalytic hydrogenation, but the type of reaction is reduction, or you call it addition of hydrogen. That's perfectly fine. So the name of X there would be what you call ethene, a 2-carbon molecule, 2-carbon alkene. They want the name, they don't want the formula. They want the reagent and condition for reaction 1. This is the elimination of hydrogen halide. So you are trying to remove HCl from your halogen alkane to give you back the alkene. You also use NaOH, but here you will see that this is substitution, this is elimination. Substitution versus elimination from the halogen alkane is a very, very important concept that get asked time and time again. You can watch my topical playlist under halogen alkane structured question. There are a bunch of questions that I chose to highlight for the substitution versus elimination kind of case study over the years, and hopefully that will be useful to you and other learners, your friends and juniors and seniors. So do share those playlists with other people as well. They're entirely free for everyone to watch. So here the NaOH in ethanol, and you also have to reflux it as well. So now suggest the reagent and conditions needed for this reduction. So we need the H2 as your reactant. Let me write that better. And you also need the nickel catalyst. And you do these at not reflux, because these are gaseous reactions. This is a solid catalyst in a different phase from this gaseous reactant. This is a heterogeneous catalyst, definition of which is required in the Redox reaction as topic. The catalyst is in a different state, different phase as your reactants there. So you need to heat it around 200 or 300 degrees Celsius will have been fine. And that's it really for this 13-mark organic chemistry question.